All right, ladies and gentlemen. 1, 2, 3, 4, 5, 6. Is Connor not with us today?
He's on the anatomy or
Okay, all three of them. Well, I did not realize that. Okay. All right, I'm going to answer any questions about homework 31 that you might have, or I'm going to answer a few questions on homework 31. Let's leave it at that. So if you've got any questions on homework 31, let's pull it out and let's talk about it there. Yeah, part 2. Yeah, not the 5 easy ones.
the one where it's like, I didn't know what to do with X. I know
Right there? Okay. All right. Let's see. Chase is here. I will not touch. Yes, I am recording now, as I am taking attendance. Okay. So how do you integrate this? Because where did you start off at, Sarah Beth? X times 2x minus 1 to the negative 1/2. Okay. Okay, so u equals 2x minus 1, 2 dx. We don't have a 2. We have this. So, what? Anyone? Right. If we take that and say u, that means u plus 1 is 2x. That means u plus 1 over 2 equals x. So now I've got a substitution I could put in there. And so you'd wind up saying 1/2. Whoops. You'd say 1/2 times the integral of u plus 1 over 2 times u to the negative 1/2 du. And if you do that, you can, I think it'll work through okay there then. So that was a tricky part. Okay. Then what can I do?
I just want to know, that's the regular equation. So how do you just regularly take the derivative of u plus 1?
No, what I would do now is, okay, I'm going to pull this 1/2 out right here. I'm going to make it 1/4 times the integral of u plus 1 times u to the negative 1/2 du. Because this right here is the same as 1/2 times u plus 1. Okay? So I pulled that 1/2 out there and multiplied it by the other 1/2 that was already out there to make it 1/4. Now, I still can't integrate like it is. But what I can do is I can now distribute and make it u to the 1/2 power plus u to the negative 1/2 power. And now I can integrate. Because when I multiply, I add the exponents. Yes, u to the 1/2 and u to the negative 1/2. Okay? Other questions on 31? Slide 9.
Number 21.
Whoops, right there. 5x and the cube root of 1 minus x squared. Okay? So what did you let u be, Mary Martin? 1 minus x squared. So that means du is negative 2x dx, and we don't have that.
You need to multiply it by negative 2/5/2.
Well, what I would do is, yes, you're going to be right there. I'm going to make it look like that. Well, that's close to what I need over there, but I actually need another 5 over there. So if I multiply, you've got two options here. You could say I'll multiply this side by 5 and multiply that side by 5. So then now I can replace this part right here with negative 5/2 du, and then this becomes u to the 1/2 power. That's one way to look at it. The other thing is you can say originally, I can just take this 5, I can just take this 5 right here and bring it out, making it just an x in there to begin with, and then you've got a negative 1/2. Either way, you're going to wind up at the same place there. I like the fact that I make everything look like it over here and then plug it back in. I think that's easier to understand. But yes, that's all you have to do for that one. And then you can finish it off from there, I do believe. Okay. Other questions about homework 31? Mm-hmm.
Wait, it was 31, the one that 31 you drew yesterday?
I don't know, sir. Check move.
31 was Tuesday, 31 part 2 Tuesday. What does it mean to solve the differential equation?
Integrate. Yes.
Okay.
That's one. Where was one? Okay. Ah, yes. 39 should have scared you to death here, okay? So it says solve the differential equations. Well, that really means that dy equals, we are still in H31, integration by substitution, part 2. No, sir. Yes, sir.
Wait, that's why I was confused, because I only did part 1 last night, and I was thinking, did I do the wrong thing?
Nope, you haven't done this yet.
Okay, that's totally.
So that's really what we're doing. We're getting everything with x's over here, and now we're going to integrate. Okay? So now, over here, the left side's kind of easy to see. That's going to give us a y. How are we going to integrate this thing over here? And we get confused because we've got this extra plus sign in here. What I would recommend that you do is simplify this or break it up. And we're really integrating 4x, and then we're integrating 4x over the square root of 16 minus x squared. We're really doing both those things.
Can I ask you a question?
Yes, sir.
What section is Cal chapter?
Don't know. 4.5, says Mary Martin. Okay, so now, are you going to need to do a u-do substitution to integrate 4x? You're probably going to need to do a u-do substitution over here, okay? But if you break it up, it makes it much easier to find out, oh, I need to do a u-do substitution. Looking at it the way it was written originally, it scares you to death with all that, and you don't have to be scared there. All right? Does that one scare you? You're going to do the same thing to it, and it looks a little scary, but it's not nearly as hard as it might seem there. So I'd rather you try that, and if you need some help, I'll help you on that some other time, okay? Yes, ma'am. Okay. All right, so you're trying to integrate it, so what did you do first? Okay, and if you do that, then you don't have a du. Then the derivative is 1 minus 8 over t, or 1 plus 8 over t squared, which you don't have out there. Okay? So, well, if you do that, then you need 2t, and you don't have that either. So this one's really, yes. If you just distribute, then you can integrate it. Yeah, that makes you feel bad when you don't see that. I didn't see it the first time I saw it either. So, but yes, you just distribute, then you can integrate just like you always have.
We don't have a u substitution.
No, you don't have to have a u substitution for this one. Actually, it'll just distribute and keep right on. I will. I guess I will. 29. Okay. So, what are you thinking there? Make this, both of them up, okay? 1 plus t to the negative 1 cubed and t to the negative 2 dt, all right? Yeah, u is 1 plus t to the negative 1. So what's du then, if I take the derivative of what I just wrote down? Negative t to the negative 2 dt. And I've got a t to the negative 2 dt, so if I just move the negative sign over, Boom. Then now I've got a substitution I can plug in there. All right? Now, once we throw the fractions in there to you, you kind of get scared of these things, and they look scary. Yes, sir? Okay. That one, yes. Ooh.
But then on the other side, depending on whether you chose to do cosine x or sine x, if you're starting, it could be plus 1/2 sine squared x or minus 1/2 sine, 1/2 cosine squared x.
Okay, I'll agree with you. Yes, you probably could wind up with two different integrations there. But end game, once you pull those in, you should wind up with the same exact thing. Okay. Yeah, you should wind up with the same number answer there. Okay. So what I heard you say is you broke this up and you integrated the first term and then integrated the second term. Fine to do that. I believe it was Mary Martin. Didn't we talk about doing this a different way than that? Okay. That's right. So if u is sine x, du is cosine x dx, and now I've got it in there, so I can make this into u cubed plus u du. And you're going to wind up at the same place you did, Chase, I'm pretty sure. When you integrate that, you're going to get to the same place of u to the 4th over 4 plus u squared over 2, which is sine to the 4th over 4 plus sine squared over 2, evaluated at negative pi over 2 and pi over 2. I don't know. That one? I don't know. We would get 1/4, 2/3, u to the 3/2 plus 2u to the 1/2 evaluated at 1 and 5? 1 and 5. Oops, we can't evaluate them yet. Got to plug back in there. Come on, Ely. So we got 1/4, 2/3, 2x minus 1 to the 3/2 plus 2 times 2x minus 1 to the 1/2. Now we can evaluate them at 1 and 5. 2 times 5 is 10 minus 1 is 9. The square root of 9 is 3. 3 cubed is 27. 2/3 of 27 is 18. Plus 3 times 2 is 6. All right, all of that minus, when I put 1 in there, I get 2 minus 1 is 1. I get 2/3 plus 2 minus 1 is 1, 2. And then take all of that times a quarter. I'm going to get a quarter of 24 minus 2 plus, minus 2 minus 2/3. Minus 2 minus 2/3. That's 22 minus 2/3. That's a quarter of, make that a 3, 66 minus 2/3. A quarter of 64/3, which is 16/3. If I did any of that right. I don't know if I did it right or not. That was, you got 4 root 5?
Yeah, I got it.
Wow.
I might got it wrong. I don't know.
Okay, but you're putting a 5 in for x, not for u.
Oh, God. Yeah.
Yeah. Okay.
Yeah.
Wait, was that the second one?
I think it is. Yes, that was the second one. Is that what you got? 17?
I don't know what I did.
All right, did you get the same antiderivative as I did? 2/3 u to the 3/2 plus 2u to the 1/2. You actually cleaned yours up more, if I remember correctly.
Yeah, but I think I just put a 2 instead of 2.
Yeah, I think so. I think that's, yeah. Okay. I think, have we answered your questions enough for you to be able to jump back on this here? All right, let's talk about, for very briefly then today, I don't know about briefly, but let's talk about two other things we've got to know. Actually, one of them today, LNs. Okay, now, if you look at the graphic that I've got here, now we're talking about 32, Wesley, integrating natural logs. If you look at these graphics, integrating x squared, x cubed over 3, we know that x is x squared over 2. X to the 0, using our power rule, becomes x to the 1 over 1. But what about x to the negative 1? It doesn't work. Because if we raise it to one higher power, it becomes x to the 0 over 0. 0 is undefined. So our power rule doesn't work there. So then we need, in order to solve this, we need to go back to our definition of an antiderivative, which is, what is a function whose derivative is 1 over x? And the answer to that is the natural log. So there's your definition, there's your rule to learn. It is the natural log. Now notice we did add in the absolute value bars around the argument.
Could you go back to the given things for the natural log?
I'm not sure what you're asking, sir. So when you're looking at this, anytime you're integrating 1 over something, the antiderivative is the natural log of the absolute value of whatever the denominator is. Now, something that students get confused on. This is just something in the denominator to the first power. It's not something squared or cubed or to the 4th power. It's none of that. It's just something to the first power. Because if it's 1 over x squared, we can integrate that using our power rule. But it's something just to a first power. Also remember to put the absolute value bars here in your antiderivative. The natural log of whatever that was. Now, it's not going to always stay that easy. We're going to have to do a lot of you-do substitutions with these. Sometimes when you look at answers, you're going to see that the absolute value bars mysteriously disappeared. It's okay if you know this has to be, for example, well, I'll point that out when we get to some like that. It'll be easier that way. So let's just take a couple of examples to look at. The integral of 5 over x. Okay? All right, if we're thinking about this, we know that the integral of 1 over x would be ln of x. So different ways you can approach this. Here's what I see when I look at this. I'm going to pull the 5 out in front, and I've got the integral of 1 over x dx. So now the integral of 1 over x I know is ln of the absolute value of x plus a c. We've got a 5 on the outside of the integral, so we've got a 5 on the outside of the antiderivative. Now, that's not the only way you could write that. You could also write it as the ln of the absolute value of x to the 5th plus c. Why can I do that? Remember, your properties of logarithms say that any number that's in front can be brought up as an exponent. Okay, so that's what we did. We took the coefficient and we made it into an exponent. Both of those mean the same thing.
So why the 5 inside the absolute value? Why is it not obvious?
It would be okay to write it either way. Okay? Either way would be sufficient there. Now you have to be careful with this, like if it was an even exponent. Because now if you make it x to the 4th, the absolute value bars don't do anything for you there.
In other words, if the number above the x is anything but 1, it's ln x to the power of the number above it.
Yes, you could think of it that way. You're going to find it more commonly written like this, I do believe. That's the most common way you'll see it written. I want you to be able to recognize that these are essentially saying the same thing there.
Like the one that I did on
Uh-huh.
FR2 was x squared minus 2 over x.
X squared minus 2 over x. Okay?
And when I integrated it, I ended with an ln of x.
All right, you can't do that because you don't have the derivative of x in the numerator. If you've got that here, was that one in the 31 homework? Okay, so then if you've got the integral of x squared minus 2 over x, in order to integrate that, I would make it x squared over x minus 2. Okay, yes, if you did that, then yes, you could integrate this second part out here.
I didn't know what to do with
Yeah.
and I realized that was not what
That's right. Yeah, yes. If you were integrating this, then you could integrate that and make it minus 2 ln the absolute value of x. All right? So, yes, that's correct. All right. So, let's look at the next couple of problems here. 1 over 2x plus 7. Is this an absolute, is this a problem to be solved with ln's? Yes. Anytime you see a fraction and the denominator is to the first power, a good guess is that u is going to be the denominator. So u is 2x plus 7. That means du is 2, which I don't have that over there, so I'll need to divide it out, equal to 1 dx. 1/2 du equals dx. And if I do that, I get 1/2 the integral of 1 over u du, which is 1/2 the ln of the absolute value of u plus c. And you could write that as ln of the square root of u. Oops, actually you'd want to do the 2x plus 7, wouldn't you? 1/2 the ln absolute value of 2x plus 7 plus c. So now, if we were integrating this, suppose we were integrating this from 1 to 7. Are the absolute value bars necessary?
Yes.
Because when I put 1 in here, what am I going to get? 9. When I put 7 in there, what am I going to get? 20. Either way, I'm going to get a positive number. So the absolute value bars wouldn't be necessary if your limits of integration are going to make it positive anyway. It's not wrong to leave it like this. I'm going to be lazy and always leave the absolute value bars there probably, because that way I know I've got it right. But it wouldn't be wrong to leave them off in a case like that, okay?
Because I'm afraid that just put it back on.
Yes, so that's me. I'm going to probably be kind of wimpy and always leave them there. It just makes more sense to me. That way I don't mess something up. All right, the integral of x over 3x squared plus 1. See if you can accomplish that without any input from me.
Would it be,
Does it not work to separate the integration into x divided by 3x squared and then x over 1?
You're saying,
Not do it like when you had that addition.
you're saying, could we do this? Okay, this is what can I do this? X over 3x squared plus x over 1. Okay. Why can we not do that, class? Yeah, we can only split it up if the denominator is one term. If the x were on the bottom, then yes, we could do that. But we can't split up the denominator. The denominator has to stay a whole unit there. So, Kevin, what do you think you ought to be?
On the bottom, 3x squared plus 1.
Very good. 3x squared plus 1. So du is 6x. So we've got 1/6 du equals x dx. So anytime you see fractions, you're hoping that the derivative is in the numerator, which is what we've got here. We've got 1/6 the integral of 1 over u du, which is 1/6 the ln, the absolute value of 3x squared plus 1 plus c. Now, very often on a problem like this, the absolute value bars would not be here, even without limits of integration. Can anybody tell me why? because we're squaring something and adding 1. So what's true of this number here always? It's going to be positive. So the absolute value bars don't do anything for you there. It's okay to leave them, but understand why they might not be in an answer that you checked from someone there.
What if your answer though was, give me a second, I was going somewhere with this.
Like if you had an x cubed in there, then you need the absolute value bars because the x cubed could be negative. Okay.
Yeah, dumb thought.
All right. Find the area enclosed between the x-axis, the y-axis, the line x equals 3, and that function. Well, we just integrated that thing over on the other page, I think. And we found out that the antiderivative was 1/6 the ln of 3x squared plus 1. So can you picture in your mind what we're trying to find the area of? What are our limits of integration? Where are we starting and where are we ending? 0 and 3. Okay? So we're going to be integrating from 0 to 3. From right here all the way out to here. And notice it says the line x equals 3. That's this dotted line right here. So we're looking to find all of this area in here.
Integration only gives you the area from the x-axis up to the line and down to the line?
Yes. The way we are approaching it right now, yes, you're correct with that.
Is there a way to approach it where you go farther down?
Yes, there is, and that's for after y'all get back from mission trip. We'll be talking about that, yes. Because all shapes don't have a nice flat line on the bottom. Bless you. Okay, so we're integrating this. There's the antiderivative. We're just bringing it over from the previous page. We're going to evaluate this at 0 and at 3. So if I put 3 in there, I get 1/6. The ln of 3 squared is 9 times 3 is 27 plus 1 is 28. Minus, what happens when I put 0 in? I get 1/6. 0 plus 1 is 1. The ln of 1. Can anybody tell me what the ln of 1 is? E to what power is 1? Yes, 0. So this winds up being 1/6 the ln of 28. I'm going to leave the absolute value bars off because I know 28 is a positive number. This is just 0. So this tells us that if we can calculate this number, that would be the area above the x-axis and below that curve there. 1/6 the ln of 28. So you've got to be sure that you brush up on that the ln of 1 is 0 and the ln of e is 1. Those are two facts you need to know. Any questions about what we did? Not hard integration there, just actually seeing the limits of integration. All right? Now, as you look at these problems, it's okay, and I caution, I'm very hesitant to say this, but I'm going to say it anyway. It's okay for you to get to a point where you skip some steps if you can. All right? For example, when I look at that problem, I can tell you that the answer is ln of x to the 4th plus 5x. Now, if you can look at it and do that, that's quite all right for you to do. If you can look at it and work through it in your head, that's okay. Because remember, in May, you're under time constraint when you're dealing with the when you're dealing with the multiple guess problems. So if you can look at that and say in your head, okay, I know that u is going to be the bottom, and so that means du is 4x cubed plus 5 dx. That's what I've got. So I'm just integrating 1 over u. So then it's going to be ln of x to the 4th plus 5x plus c. You need to get to the point where you can look at that problem and know that that's the answer. And not write down any of the U part that I did, and not write down the integral here. If you need to write it down and want to write it down in homework, I encourage you to do it. It's going to help you to learn what you need to be doing. But you want to be working towards not having to write down everything there. All right, let's see how many more problems we want to look at here. Just a few more, I think. 8. Oh, yes. Throw some trig in there. Does that bother us? Okay. Anytime you see a fraction and the denominator is to the first power, I want you to think ln's. Okay? If I let u be the tan, then what's du? Secant squared. So I've got my du up there. So you probably can look at this and say, then that's going to be the ln of the absolute value of the tan x dx. Plus c. Thank you, sir. Yes, that's points off. We don't want to miss those points there. So let's just look at these others. Is there anything that scares you there? That's just like one we worked just a moment ago. Has a 1/2 in front, but does that scare us there to see that we're going to have the 1/2? This one's a little bit more tricky because of that 5 up there. This is kind of like the one that we started off the day with. What I would recommend doing for this, I'm going to pull the 5 out and integrate this. And if we do that, then we're going to wind up with 5/2 the ln of 2x plus 5. That's really what it's going to wind up. As long as this is, yes, that's what it should wind up being there. So it's not the hardest thing we've done here. I think y'all have a good handle on it till we throw you something like this. This might throw you for a loop. dy over dx equals 1 over x ln x. One over x times 1 over ln of x. That is definitely legal to do. I don't know. All right, so you think u-dos. Do you see a u and do you see the do for the u? Do you? Yes, we can take an ln of an ln. Yeah, sure. It's called ln squared. No. So where are you going with that, Chase? No, it's not. No, it's not. I was bad math humor. So where were you going with that? You were going the right place. The derivative was going to be 1 over x, but then put ln to the bottom power, and then you multiply by 1 over x anyway, which is 0. Yes, sir. You got there. Okay. What did we say? Normally we want the denominator to be our derivative. If we let our u be x ln x, there's no way we get to that derivative. Okay? So, if we let u be ln of x, then that says that du is 1 over x dx, right? And now, look at what we have. We have a 1 over x and a dx right here. So now when we integrate this thing, we are saying, well, we can put du in place of all of that. 1 over u, because ln of x is u. Yeah, u is ln of x. Now, how do we integrate 1 over u? Well, that means it's the ln of the absolute value of u. Bless you. Bless you. But what is u? Bless you again. It's the ln of the absolute value of the ln of x. They were not in there originally, so we don't have to put them in there. It wouldn't be wrong to put them in. It's not wrong to put them in, but since they were not there. actually, we don't even have to have the
Why don't we just add outward absolute value thing? So it's that obvious to be sure, ln is the absolute value, ln x in absolute value?
say that again? You lost me.
I thought it was gonna be a lot more complicated than that.
Nope, it's the ln of the ln of x.
I could read it like that.
That would be simple enough.
Does x have to be a positive number? Does second?
We can assume from here that x is going to be a positive number, because x being a negative, x being a 0 or negative number in the original equation makes no sense. So the domain, since nothing is stated, we're going to assume that the domain is x greater than 0, which means then that this number ln of x is always going to be positive. So we could really just write it as ln of x plus c. Ooh. Would this be wrong? Chase immediately says no, and then he says, I'm not sure. Can LNs be negative? Ooh, good question. Nope, LN. No, an LN. Yes, you can't have an LN. You can't take the LN of a negative number, but the LN of a number can be negative.
As long as ln of c can be all values.
Yes. Yeah. LN of C can be all values. So there'd be nothing wrong with this answer here. Y'all comfortable with that? Because C is just a number. Yeah. We could, yeah. As long as it's a constant number. That's right. As long as it's a constant number, we can name it however we want to. It's just like your children. You can name them however you want to, okay?
Like Star Wars.
Yes.
They're tortured their whole life.
Yes, you could do that. Integral of tan.
Oh, it's like cosine over sine, or sine over cosine.
Yes. Now, when you look at this, there's no fraction there. So, but there is a fraction there. If we integrate it, it's the ln of sine x over cosine x. So integrate that and see what you're going to wind up with. Hello? I am fine. I do. Yes. Yes, I do. No, I've got them on right now.
You're still writing it through.
All right, thank you. Bye. Mary Martin, you are needed in the high school office. So now, if we are going to integrate this with what we've been saying, we would say the ln is u is a cosine of x, so du is minus sine of x. Agreed? So minus du equals sine of x dx. So that means we're integrating minus 1 over u du, which is minus ln, the absolute value of the cosine of x, plus c. Is the absolute value important there? Because cosine could be positive or negative, right? Yes, sir.
Is there any case where you absolutely have to use substitution and you just can't kind of like do it another way?
Next year there is. Okay? No, you're doing substitution. You're just doing it all in your head up here, sir. You're doing it. I can hear the words that you're saying, you are getting to it. You're just doing it all in your head, okay? Integration by parts, that's something that's a little bit that you'd have to do on paper. But I think you're doing substitution fine in your head there.
The cosine is like sine x equals cosine, you know.
So why is it why is the bottom part, right?
Or say that again now.
I mean positive sine x is pretty.
The derivative of cosine is minus sine. The derivative of sine is cosine. The derivative of cosine is minus sine. So since we're letting u be the bottom, cosine. Yep. Since u is the cosine, du is minus sine. So the integral of tan. Yeah. Now, Any questions about how I got there? Everybody's just off on their own tangent there. Okay? These are 6 trig rules for integration. You can get to all of these. You can get to all of these by using you-do substitution. Well, the first 2 you already know. The third one we just did. These last 3 you can get to by you-do substitution. I don't recommend it. I just say kind of refer back to these if you need to. I would say, obviously, you need to know these 2. We just did that one. If you know those 3, I think you're going to be in pretty good shape. The others, you may have to find them sometime, you may not. But what we just did is just really come to this conclusion right here of finding that rule there. So, in the derivative of sec tan, so the antiderivative of sec is the ln of sec tan. How about that? The derivative of cosec is cosec cotan. The antiderivative is minus ln of cosec cotan. I just saw that. First time I've ever seen that. So that may help you to memorize those if you choose to, though. I'm confident you all have great abilities to solve these problems. I'm not going to waste our time doing any more of them, okay? You have the balance of the day to work on whatever you think you need to be working on. Some of your homework, some of your FRQs, some of your web assigns.